All right. So I wanted to make a supplemental video about ammonia and ammonium hydroxide since we used it in this past lab. And the lab manual wasn't very clear on why they're exactly the same and why you could just write ammonia as opposed to like ammonium hydroxide and what was happening there. So to start off, let's look at what water is. So water, we have HOH, and we always draw it in this bent conformation because of the lone pairs, and that's how we make it all 2D. Now we know that oxygen is the second most electronegative element, and that means this bond, while it is a covalent bond, the electrons aren't necessarily equally shared. They're going to hang out more next to oxygen because he's just stronger than hydrogen is. And so, quick review of this symbol here means partial. And so you can have partial negative and partial positive charges. And that's when, you don't have like a full like extra electron sitting somewhere, but just because the electrons are being pulled more one direction, it's going to make it a little bit more electronegative. So I'm going to put partial negative, partial positive, partial positive. And this is what it means when we talk about polar molecules. This doesn't have like a full negative charge on him. It's just he's a little bit stronger than the hydrogen at pulling electrons towards him. And so he's going to be a little bit more negative than the hydrogen. But what does this mean for the overall molecule? It means it's a magnet. It's got like a north and south pole, essentially. It's got a positive end and a negative end. And that means if we start drawing multiple water molecules, they're all going to want to line up in a very specific way. So you're going to have another water molecule here. He's going to have a lone pair of electrons. And since he's got a little bit of a partial positive and he has a partial negative charge, they're going to line up. And these lone pairs are actually going to form something called a hydrogen bond. It doesn't mean that this oxygen has fully ripped away that hydrogen, but they're going to coordinate and line up just so perfectly. And this happens throughout all of the water. I know these are going to look like eyes to you because of how I'm writing them. So I need to write an eye to me. I'm sideways there. Now they look like H's. Hydrogen bond. Now, the other interesting thing that can occur is these molecules, they're constantly flying around and crashing into each other. Sometimes they're going to crash into each other with such force that this oxygen is actually going to be strong enough on a rare basis to rip this hydrogen away from it. And when that happens, we're going to end up with H, so that, and so here, oxygen with 3 hydrogens, oxygen with 1 hydrogen. So we're missing a whole bunch of electrons. So 1, 2, 3, 4, 5, 6. This thing has a negative charge. Over here, this thing will only have a single lone pair now because one of its lone pairs, when it collided with a hydrogen, decided to rip it off. And this thing will have a positive charge. These are full positive charges, not partial positive charges, because the entire charge of the atom is different. Oxygen is in the 6th column, meaning it likes to have 6 electrons around it. He has 1, 2, 3, 4, 5, 6. And in this bond, there's 2 electrons. And one of those electrons is oxygen 7. Oxygen likes to have 6 according to the periodic table. Actually, he likes to have more, but according to be neutral, he has to have 6. Right now, he has 7 electrons. That extra electron makes him negative. Over here, water likes to have 6. 1, 2, then one from this bond, one from this bond, one from this bond. He has 5. He likes to have 6. That means he's got a net positive charge on this oxygen. And this is something called equilibrium, where it's constantly just going back and forth. And the way that you can think about equilibrium is like a big game of dodgeball. There's a fixed number of balls on the court, and they're constantly being thrown back and forth, back and forth, back and forth. If one team is stronger than the other, they're going to throw the balls, and they're going to mainly statistically be on one side of the court. Now that other team that's weaker, they might periodically throw some over. But it's just a big dodgeball game. Things are constantly in motion. Nothing is ever like frozen, maybe at absolute 0, but that's not what we need to talk about. So that's what's happening. Now, we used ammonium hydroxide in lab. And ammonium hydroxide is simply ammonia in water. And I'll show that. So if ever you want to work with ammonia, you're actually going to have to buy ammonium hydroxide, or maybe there's a way to prep just the ammonia in absence of water. But when you buy it, you buy ammonium hydroxide or ammonia. They're basically the same thing. The reason for this, again, these things are constantly in motion. So nitrogen, when it's called ammonia, has 3 hydrogens. Now nitrogen has a lone pair. So it's like that. And we again have water. I should make this different. Now, water again has lone pairs. And when they're in solution, they're going to, again, line up. I could have done a better job of doing this. I'll put an oxygen here, hydrogen there, a hydrogen there. And again, this oxygen has a partial negative charge. Hydrogens have partial positive charges because oxygen is more electronegative. Oh no, my son's waking up. I'm running out of time. So that means nitrogen is similar. It's not as electronegative as oxygen, just because we're shifted over one column on the periodic table. We know that the trend is fluorine is the most electronegative element that there is. So it's not as strong as oxygen, but it still is. And so that means nitrogen would also have a partial negative charge, and its bonded hydrogens would have a partial positive charge. And with all these things working out the way they are, they're going to form hydrogen bonds, where they're just going to sort of line up, kind of like if you put a bunch of magnets and you threw them on a table and shook them up. All those north and south poles, all those positive and negative ends, they're going to line up. That's just how it's going to be, and that's how it is in solution. Now, occasionally, these things are flying around super fast. They're going to collide into each other with enough force and actually cause things to happen. Now, this is a very important question, because someone asked, and it was a great question, like, how do we know what's going to happen? A lot of that comes with practice. In chemistry, for the most part, we're going to tell you what's happening. We're going to learn these different reactions and have to redo it. But it really comes down to who has electrons and who wants electrons. Who has electrons? Who wants electrons? These questions, please start asking yourself these questions, and you'll start to understand a lot more what's happening and why. Oh, Calvin's waking up. So who has electrons? Oxygen and nitrogen both have electrons. They actually have spare electrons in some sense. They've got these lone pairs sitting there. Who wants electrons? Well, that's the hydrogens. They want electrons. And what we're going to have to think about is who wants actually electrons more. And that's oxygen. Like, if oxygen has a choice, he wants electrons more than nitrogen. So what would happen if Oh, Calvin. Sleep a little longer. Put a hydrogen right here and hydrogen right here. So what if this water molecule and this ammonia were to collide into each other with enough force that instead of forming just like a little like temporary hydrogen bond, like it actually causes this nitrogen to rip it off. And why is it going to rip it off? Because oxygen actually wants electrons more than nitrogen. So he's like, I want to keep these. So these two electrons here would end up staying on the oxygen, and these electrons here would end up grabbing this hydrogen. So we're going to do a little thing here. We're going to make another bond to this hydrogen. Nitrogen is going to use both of its electrons to form this bond. These electrons here are going to stay on the oxygen. I never drew oxygen's original two lone pairs. Now, what do we have here? Oxygen, it's in the 6th column, but yet it has 7 electrons around it right now. So it is a minus charge. Nitrogen, instead of being ammonia, it's now ammonium. I think I have that right, ammonium hydroxide, yeah. And it no longer has that partial negative because it's actually got a full positive charge now, because nitrogen likes to have 5 electrons around it because it's in the 5th column. And right now it only has 4. 1, 2, 3, 4. So it has a net positive charge. Again, these aren't partial charges, they're full-on charges. Ammonium hydroxide, it just comes from ammonia, NH3, being mixed with water. They're going to start bouncing around, they're going to collide. Some of them are going to collide with so much force. And since oxygen wants electrons more than nitrogen, it's going to be more than happy to be like, dude, I'm going to be a negative charge. I'm just going to be a hydroxide ion. You got to carry this extra hydrogen for me. And nitrogen's like, okay, whatever. I've got extra electrons, so I can do that. So ammonium hydroxide is flying around. Now, occasionally it'll be bouncing around, and this hydroxide might collide into a different hydrogen and it'll go back. And this is that dodgeball game where things are constantly going back and forth, back and forth, back and forth, and constantly changing. So this is why, if I can finish this all up. NH3 plus H2O will go to NH4OH. I ran out of space, I can't really go horizontally, but ammonia plus water is going to give you ammonium hydroxide. So in lab, we were using ammonium hydroxide. And then in some of the equations, it was just showing ammonium. It's because all these different things are in the solution at the exact same time, bouncing around, going back and forth, always changing who's holding on to that extra hydrogen. Is it the nitrogen that has, or is it the oxygen that has the hydrogen on it, or does it occasionally pass it off to the nitrogen? And it does go back and forth. Now these arrows, you'll eventually learn them. Hopefully you've seen them before. But basically what this is 2 arrows. So we know that this reaction occurs like that. That is occurring. But we also know that the reverse reaction can also occur. This isn't true for all chemistry equations, but for something like this where it's in a balance, it's called equilibrium. Oh, Calvin is definitely saying, get me up, daddy. So that's why you end up doing these 2 half arrows saying the reaction goes this way and the reaction goes this way, called equilibrium. Awesome. That's it for now. Let's see if I can make another video with my son.